Hey YouTube, my name is Rob. I'm a data scientist and Kaggle Grandmaster. And in this video, we're gonna learn about how to do machine learning from scratch. We're launching a brand new series of competitions on Kaggle's community section called the PogChamps series. And I really hope you can join us. In this video, I'm gonna go through a baseline submission to the very first competition. It's gonna be really awesome, and we're gonna learn a lot about how to create models and how to code in Python. So with that, let's get started. Okay, here we are on the front page of the PogChamps series Kaggle competition. Isn't it beautiful? If you look here, we have some description of what the competition's about, the valuation metric that we're using. But don't worry, I'm gonna go through all of this in detail. Let's just jump over here to the code section. And there are a lot of notebooks here, which are nice, but we're gonna jump into my Pog on YouTube lightGBM baseline model and take a look at that code. All right, so we're editing this notebook and I'm gonna step through it line by line so we all know what's going on here. So the competition here is based around trying to predict for YouTube videos what the like to view count ratio is. So I'm gonna load in the data here. These first lines are just some imports that we have. Let's let the notebook start up. If you don't already have a Kaggle account, you can create one for free and you can join our competition and you can be on the leaderboard in no time. So while this is running, I'll just jump over here to this competition and show you that there is a leaderboard where we can track and see how well everyone's doing. And if you submit, you'll be on this leaderboard too. Back to our notebook. Okay, so it's loaded up. We're running this first cell that basically does all the imports of libraries that we're going to be using for this competition. Pretty straightforward. We have pandas, which we'll use all the time, NumPy, Matplotlib and Seaborn for plotting, and then we have from Kfold for doing cross-validation, and we have lightGBM, which is the main model that we're going to be using in this baseline notebook. We also have imported from sklearn mean absolute error. That is the metric being used in this competition to judge who has the best submission. We're also ignoring some warnings because there were warnings that were causing me issues. We're gonna load in our train, our test, and our sample submission file. The train and test files are saved in Parquet format, so we're gonna read them in using pd.readParquet, and the sample submission is a CSV, so we'll read it in with read CSV. There we go. And I'm just gonna show you after that loads the first 5 rows of the training set for this competition. All right, so what do we have here? We have a bunch of information about YouTube videos. The published the video ID is a unique value for the video itself. We have title, which is the title of the video. Published at, which is the date the video was first published. Channel ID, which is unique, also with channel title for the channel that the video has been posted at. Category ID maps to the different type of category in YouTube, like entertainment or educational, those sort of things. Each of them associated with a number in the category ID. Then we have the trending date. This is the date we're trying to predict what the view count to like ratio or like to view count ratio is for that given video. We have the tags of the video. We have the actual view count in the training data set, the like count, the dislikes, comment count. What else do we have here? We have a link to the thumbnail. We actually provide you all the thumbnails for these data rows that you can use to train your model to try to get the best submission. True or false if comments or ratings are disabled. And then the full description. This is the full text you'll find in the YouTube video underneath the description. Now this ID column is a combination of the video ID and the date. this ID column should be unique for every single row in our data set for both train and test. And then we also have, for some of the videos, the length of the video, so the duration in seconds, and true or not, false. Now this last column is the most important one. That's our target column. That's what we're trying to predict. And if you look here closely, let's just subset to view count and likes and target. If you look here, the target value is actually likes divided by view count. So if I just take likes here for this first example and I divide it by the view count, we should find that the target is that value. And that's true for this whole training data set. Now for our test data set, you can see it has all the same data columns that we have, with the exception of the views, the likes, the comment numbers, any of the information that we would consider to be in the future that we don't want to give you to allow your model to need to predict this target instead of being provided it by our test set. So that's why some columns don't exist in the test set. So we know what we have. We know what we're trying to predict. We're trying to predict the likes to view count ratio of every video. Why don't we get an example before I go too far of, in the training set, what the distribution of the target looks like. So let's plot this and let's make a histogram with 50 bins. Bam, there we see that there's a distribution that's kind of has a long tail out to the right, but the values that we'd be guessing here is between 0. That means there were 0 likes in the video, all the way up to 0.3, maybe even 0.4. So that means almost half of the views of the video, or 0.4%, 40% of the views of the video also had likes associated with them. Interesting. Not to get too far into that, you can explore the data all you want on your own later on. Next thing we're going to do is start creating our machine learning model. But before we do that, we want to do something called cross-validation. Why is cross-validation important? It's important because otherwise we're just relying on the leaderboard to see if our model is actually improving. And when we use cross-validation, we actually take our training data, which we know the labels to, we know the target to, and we slice it into separate sections. And then we can hold out those sections and check to see if our model is doing a good job predicting on them or not. So the type of cross-validation that we're going to do is k-fold cross-validation, where we're actually going to split the groups of our training data by the training video ID. Remember, there could be multiple video IDs in the training set or in our test set, but they would be for a different date that we're predicting. So the same video may be trending 5 days in a row, and we need to predict this ratio for all 5 of those days. So how are we going to create the folds? Well, we already imported from model selection k-fold, and this actually allows us to easily split into these 5 different groups. So running this k-fold with the number of splits that we've configured, we have our configuration dictionary here that kind of stores some of the variables we'll want to come back to later on. But we have 5 different folds that we're going to split our training data into, and that's this number of folds or number of splits. We're going to shuffle the data around before we split, and then we're going to feed it a random state. That's just a random number that we can use for reproducibility. That's our k-fold splitter, and then we will iterate over this k-fold split 5 times, and we'll add to our training data set a new column with the fold number. So I'm going to run this and actually show you. Now in training data set, we have a fold column here. That is a number between 1 and 5. If I look at our fold column and do a value counts, we can see in each one of our folds, we have around 18,000 videos that we're holding out. There are no overlaps of videos in each of these folds. Each fold should contain all the rows for each video. So training data set, we have our folds. Another thing we can look at is just, I think that's good to understand how the folds work. Moving along here, we are going at lightning speed here, so I hope you're listening. We're going to talk about feature engineering. What's feature engineering, you say? Well, we have all of this training data. We have numeric values, or categorical, I guess, with the category ID. But we also have things like dates. And we can create features that are relationships between different features in our training data. And we've done a few of those here. So let's look at the first ones. The video age and seconds. So we've taken the date that was published, the date that the video is trending, and the difference between those is going to give us the number of seconds that the video has been available. That's going to be a very interesting feature to see if it helps out our model. We're also pulling out the day of the week for the trending date and the date that it was published to see if those help. Let's take this category ID. This is what we're doing here, taking that category and we're making it as a category type. This will make sure the model knows that this is not a numeric value, but each number is representative of a different category in our data. So that's important. Then we're taking the channel occurrence. So this will add a value to every row in our data for the channel ID in that row. How many times does it occur in the training and test data? Similarly, we're looking at the unique video count for the channel. So if we have a channel with 50 separate videos that were trending, this value would be 50 for that row. Or if it was only a channel that had one trending video, it would be 1. The way we do that is we group by the channel ID, we find the number of unique videos, and then we map that back to this channel ID in our data frame. Finally, we're gonna find the video occurrence count. So this is the number of times in the data set that we see this video. And we're gonna rank it so it'll go by first time it appears in the data set all the way to the end. So if it's the first time the video appears for a given date, it'll be 1. And then the more days that it appears in the data set, it'll increment up 1 by 1. So we created this as a function here, create features function, and I'm just gonna run this cell. What is this doing? This is taking our train and our test set. We're adding a column called isTrain, and this will just let us keep track of what's the training part of the data, what's the test part of the data. Remember, the columns are almost identical in these, with the exception that the test set doesn't have any of the solution values like the like count or the view count. We're going to concatenate those both together, and then we're going to run our features, and then we're going to split it back out into training and test set using this column we created here. All right, very exciting. I'm going to run a head command on this training data set. We have everything that we had before, plus, where are they? Oh, I ran it on the wrong thing. The train feats output. We're gonna run this, and we have all the same features as before, plus these new ones we created. The video age and seconds, the trending day of week, the published day of week. Now these are both also categorical variables. Our channel occurrence, the channel unique video count, and the video occurrence. So all of our features look pretty good in this data set. Now we're going to just define two things. A list of features. These are the things that we want to provide the model to help it predict our target. And then the target column, which so happens to be target in this case. And then we're going to separate out all the data we want to use as the training data. And we're also going to create what we called out of fold data frame. I'll get to this later. So this line of code just takes our test features, creates a test target data set, and creates our out of fold and our submission data frame, which we'll eventually use to submit to the competition. Just to show you here, X test does have all the columns that we've identified as being features up here. And that's it. We don't have any target for it. All right. The next part is going to get a little bit complicated, but stick with me. What we have here is our model that we're creating. It's a lightGBM regressor model. lightGBM uses gradient boosted trees as the type of model that it creates. It's a very robust model that can handle null values. It can also handle numeric, categorical, or ordinal features. It's fine with all of those. And it's generally just a very robust model to use out of the box on tabular data. Gradient boosted trees, the way they work is they build decision trees, and it grows the number of decision trees that it makes to try to reduce the loss function as much as it can. So each tree that is built is trying to find the way of making the model even more and more hyper focused on reducing the loss in the loss function that we're providing it. And we're going to provide it mean absolute error, which is the scoring algorithm used in this competition. So we're creating a few lists here. This is a list to hold each of our models, and this is FIs is a place to hold all of our feature importance variables. And then what are we doing here? We're looping through each of these folds, 5 different folds that we've split our data into. And we're going to each time take out one of those folds and not train the model on it. Hold that out just to predict on to see how well our model did. The other 4 folds we're going to use to train the model on. And once we've done that 5 times, then we've done our full cross validation. We're creating our training data set, our validation data set, and targets. And then we are creating our model here. We're going to fit the model on this data, and we're going to use something called early stopping. What does early stopping do? It stops the model from overfitting by halting it as soon as it sees that the loss function is not improving on the validation set. We are also going to make it verbose so that every 200th tree, we see what the error value is. And then we're going to predict on the validation set, and we're going to score it to see how well we did. Remember that out of folds data frame that I created? The out of folds is just a storage place where we're going to store all of our predictions from each of these folds. So at the end of it, we'll have predictions for all of the training data set because we trained 5 models and predicted those 5. We're also going to grab out of the model the feature importances. Now with a nonlinear model like this, we don't have a direct relationship between each feature in our prediction, but we do have a nonlinear relationship that we can articulate through feature importances. And the type of feature importances we train this model to show us is gain. So that means it'll show us for each feature how high up in each tree does it appear when it appears in a tree that the model has created. This is our feature importance data frame that we're saving off. And then finally, we'll predict on the test set, and we'll store off that prediction to use later. Stick with me. I'll run this. We'll check it out. All right, so we're running for our first fold. We can see our validation score is getting better and better. Each value here on the left is showing the number of trees that the model has created. And at a certain point, it stops because of our early stopping. It says Okay, at a certain point, we've actually started getting worse on our validation set. So we'll stop there and not continue on any longer. And it's same thing for our second fold. The values for score for each fold is going to be slightly different each time. Let's see how this runs for fold number 3. Fold number 4. Exciting stuff here. And our final fold, can it do it? Yes, it is going, and it is running that final fold. It is running that final fold. And I just realized here, there's a bug in this code. So at the end of each, it's not a big deal, but at the end of each fold, it is printing out the incorrect score. We'll just change it here so next time that won't be the case. It's a little odd here because I was noticing the score of the fold was the same each time, and it shouldn't be that. This should be a separate number, but let's just ignore that line for now. So we've ran all 5 folds, and now we actually have our out of fold data set. Remember, this is all of our targets and our predictions from those out of fold predictions on our training data set, and we can score the entire training data set on how well we did with our out of fold predictions. Let's do that. Oh, our score is 0.0185. Looks pretty good. Looks pretty good. I think that's good to submit. And remember, we also created this submission data frame that stores our test predictions. So each time we looped over, we also stored out our test predictions that we're going to use for our final submission. So whenever we're training our model and trying to improve it in the future, you want to make sure trying to get this out of fold score to improve. The leaderboard score is something to sort of rely on, but the main thing you want to be focusing on is get that out of fold score better. Trust your cross validation, as we say. I'm also going to plot these feature importance so we have an idea of what features the model is using more than others. So we can see here for the gain importance, duration in seconds is important, followed by category ID, so the type of video it is, entertainment or music or those sort of categories. Channel occurrence, so the amount of times the channel appears in trending videos. The unique video count, age in seconds, okay, and then down here, things like comments disabled really don't affect the model very much. So this gives us a good idea of what's the most to least important feature in our data set that we've created. You can create a lot, there's a lot more features you can think of creating on your own. And the last thing we're going to do with this submission data set is actually make it ready to use for the competition. So because we predicted on our test data set, each fold, we have 5 different columns that we've predicted. And we want to take the average of these 5, which will be our final submission prediction value, because you can only predict one value per row in our submission data set. So that's exactly what we're going to do here in this next line of code. We take all the prediction columns, we take the average value, we store it in target, and to make things pretty, we're looking at the correlation between each folds. We would expect them to be somewhat correlated, but a little bit of difference because it was trained on slightly different data. And around 0.94, 0.95 correlation looks pretty good to me between the different fold predictions on test. And the last thing we're going to do is save out this submission file to CSV, and that's it. Now let's go back to the competition. If you look here, this submission actually scores on the public leaderboard 0.01791. Yeah, that's right. And that's a pretty good submission, baseline submission. If you were to just go onto the Kaggle competition website. Click on this notebook, Data tab, download this file, and submit it to the leaderboard. Let's see how you'd be doing as of today. You would be doing pretty good. You'd be in the top half of submissions. So that's even more reason why to join the PogChamps Kaggle competition that we're launching. Also, follow me on Twitter and Twitch, where I stream from time to time. I'll have more videos like this. I go a little bit slower paced and talk through with the community what questions you might have. And I hope to see you around the leaderboard. Have a good one.